Blackbody radiation, poem by Ankur Ghosh. Blackbody radiation in cavities in theoretical situations. We can find its intensity using Planck's distribution. But don't jump to conclusions. Remember your assumptions. Black bodies aren't around us, they're theoretical illusions. The more you look, the more you see delta max and T are factors of C3. Plug one in and chug one out. Wien's displacement law will sort it all out. Radiation is a transfer of energy, but nothing radiates like a black body. It's power emissive and quanta of energy, but its mysteries soon meet their greatest enemy. His name was Boltzmann, and he left us with EB. All right, that was actually a pretty informative poem, I thought, compared to some of the other more abstract ones. This one may not have been the greatest literary piece, but I think it explained things fairly well. Which, by the way, if you did not understand what that meant, that's fine. We are going to go into it. But first of all, what are you watching?
That's what I want to know.
All right, the mysterious voice in the background wants to know what you're watching. You can see on the bottom of the screen, you're watching SG2 on Space, the only weekly space show. If you're watching this live, we're now doing this on Tuesday nights at 6:30 p.m. U.S. Central Time. So when I say Tuesday night, I mean, our local time, 6:30. You can find it on youtube.com/@Shinga/streams. For the latest episode, you just click on and all the the previous streams, the past episodes as well. And you can also search for SG2 on Space on YouTube to see a number of videos back when I was with Action One Media. So without further ado, let me bring in the disembodied voice, which is there. I did it backwards.
Now I'm an embodied voice.
The embodied voice is here. So SG2 on Space, right? So how are you doing, Leonard? Oh yeah.
I'm doing great, as always.
As always. Okay,
Yes,
I'm glad to hear that you're doing well.
How are you doing?
I'm doing all right. I'm getting kind of hungry, but that's something to do after the show. So before I go on, I do have to say, hey everyone, support the show, patreon.com/SG2 on Space, and of course on YouTube, like, subscribe, and all that. Unfortunately, I still don't have the Facebook access. So whenever Facebook will ever respond to me, I will get that and then tell you guys about it. But for now, definitely just go on YouTube, and that's where you're watching the show, hopefully. Thank you for our past supporters and patrons, Kyle Baker, Sam Welsh, and Tim Rao, the last of which did not financially contribute, but spent a whole bunch of time helping us produce the show for like a whole year and a half, which is great. So with all that said, blah, 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 let's jump into this episode, which, what are we talking about today?
What are we talking about?
Okay.
The financial crisis, or?
Not quite.
This poem. This poem was, I actually kind of like that poem.
Yeah. It has a number of things which I'm like, if you're not a physicist, you have no idea what it means. Like, what is well, first of all, let's just start from the basics. What is a black body?
What is a black body? Okay.
Yay.
Well, let's see. This takes us back into history, to maybe the latter part of the 19th century, before quantum mechanics, and we hear this all the time. What's a black body? And so back in those days, the idea. Precise measurements of light were coming online. We were able to measure the intensity of radiation at particular frequencies and so forth. And so the notion, or the physics that gives hot things color. In other words, when everyone has experienced this idea that as you heat a piece of metal or something, that as it gets hotter and hotter, it will gradually start to glow. You'll start to perceive red, and then if it gets hotter, then it gets to be yellow, and maybe hot enough, it will glow incandescent. It will be white hot. So just like now it's the old-fashioned kind of light bulbs with a filament in it. And so scientists in that era, at the end of the 19th century, really the 1890s, were wondering about that phenomenon, and they had some good classical physics that said that when when electrons or charged bodies, actually electrons had not really been discovered at that time, but they knew that they treated the object like a cavity kind of situation where the waves, they knew that light was a wave and that the waves would arrange as multiples of the interior parts, the interior elements of a body. So for example, we have like a metal shell, and you heat it up to a certain temperature, then the thought was that the radiation would have modes. In other words, there'd be a wavelength and then a shorter.
Hmm.
And at the same time, there was this I've forgotten who came up with this equipartition principle, whether it was Jeans or Rayleigh or um, but uh, we had discovered this idea that there's a equipartition principle, which means that if something is in equilibrium, if something's in equilibrium, then all of the ways that the all of the modes that can be exploited by the energy as in a certain respect would be divided evenly. So for example, if I have something that can vibrate in a like a string, like uh, a vibrating string, well, the energy of the vibration would distribute among all of the modes that that string could exhibit. And likewise, it was thought that the radiation would distribute in that matter. So there'd be some kind of like a fundamental mode, and then a secondary mode, and then a tertiary, and all of those modes, they would all be populated because of this thing called equipartition principle.
But before you go on, what
Yeah.
what what is this was a theory that was the
This was a classical theory that
the
was
classical theory. So
the
we haven't
classical
reached the
theory.
quantum mechanics yet. All
Well,
right,
yeah.
go
So
on.
this was the classical theory, was that the energy of the radiation would be distributed equally among all the modes that it could exhibit itself, or manifest itself. And so these two scientists, Rayleigh and Jeans, sometimes it's Jeans, I don't know how to pronounce his name. The two of them together use the classical theory to try to theoretically predict what was the distribution of radiation as a function of frequency, or you might say as a function of color. Um, the different colors at different at uh, intensity as a function of color. What would that look like according to this classical theory? And they came up with I don't we need to get some visual things that we can show somehow, but or some kind of palette that I can draw on. Maybe we work on that. But it was effectively a quadratic. It was well, yeah, there it is. So there, perfect. Boy, you work fast. That must be Wikipedia. So you see the dotted line for a particular um, uh, um, um,
I do
temperature.
work fast, and what are
Yeah.
we looking at?
Well, this is the distribution of intensity of radiation from a hot
Hmm.
object. It's a very hot object. I think that's the sun.
5800K.
Yeah,
That's kelvins.
and
That is the sun.
yeah, and this is a function uh, of frequency, and right in the middle of that that's probably visible, where the pattern, where the curve, the blue curve, is a maximum. That's
Hmm.
that's roughly within the um, visible visible range. But the Rayleigh-Jeans theory, which was classical, matched very well at low frequencies. And here, and you can see near zero the Rayleigh-Jeans, but
Right.
it went because they had no idea, no limiting size for the modes. There was nothing to limit that. um, and I remember doing this calculation in graduate school, where would we actually use the equipetition principle and then presume that you could have as many modes, infinite number of modes. In other words, you could subdivide them infinitely to
Mhm.
to infinite, and that's how we think of a continuum. Like the classical theory, everything's a continuum. So this theory would go off to infinity,
You
and
can
I
see
think we
that it just very quickly does, actually.
yeah, it
Right.
well, for this scale and so
Right.
forth. And so um the notion so what happens there is that um this was referred to as ultraviolet cascade, or ultraviolet
Catastrophe.
catastrophe. And the reason they thought of it as a catastrophe was it's a good thing that things don't behave that way, because it means would be radiating um everything would be radiating in the ultraviolet, or there would be even some x-rays, and higher frequency gamma rays would be coming off of things, because this theory is predicting that the intensity at the highest frequencies would be maximum. And so this was a really serious conundrum at the end of the 19th century, because it was showing some cracks in the classical theory. And Wien's there is also this Wien. So the classical theory is wrong, okay, and there it is. And then you see in the where Rayleigh-Jean's law, where the intensity of the radiation is proportional to the square of the frequency. And so that actually describes a parabola, a parabolic. But
The 8
mhm,
pi, let me see.
yeah.
You see that, right? 8 pi, whatever,
Right. Well,
v
that's all.
squared over
Those are
c
yeah.
cubed.
Those are all
Yeah.
constants, and so it's proportional to temperature, um and proportional to the frequency squared, to the square of the frequency. So as the temperature increases, everything all moves over to the right. It gets higher, higher. So so so
Mhm.
what Planck did. Uh, Planck was messing around with this equation, and so just was he was what he thought was, well, let me see if I can like put a lower limit on the number, on the energy, on the modes that can be expressed. And he came up with a similar kind of equation. It's still proportional to the square of the frequency, but it has that other term that has a constant in it, and we call that constant h. Or and
Planck's constant.
yeah, and it ended up being called Planck's constant. So that's
He
the
he
famous Planck's
w
constant.
Right.
Eh,
And so the Planck's law there looks like the only thing that's different is instead of multiplying by kT, you're multiplying by h nu over e to the h nu over kT minus 1.
Right. And so what he's the principle there is that and this is a result of doing some infinite series, and then figuring out what they're equivalent to, and so
Mhm.
forth. And I don't think I could do it today without looking at my notes, but I do remember doing this in graduate school.
Can
Uh,
derive it.
and yeah, deriving this in graduate school. Don't ask me to do it now, but I mean, it's not I don't recall it being a terribly difficult problem. It's been so long, and I'm rusty. But
The
the
derivation of Planck's formula.
yeah, so the bottom line is that the physics that he introduced was that there is a minimum there's a minimum energy that can be expressed by by a mode in one of the modes, and that energy is quantized. In other words, the 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 amount of energy that can be exhibited or expressed is the equal principle is still prevailing, but the energy can only be expressed in quanta, and I think that's even where the term quantum came from. So now Planck was not, my understanding of it is that Planck, I think that they thought there was some deep physics here, something
Right.
very profound that was going on. Although he originally, I think the way he expressed it was that the that it was sort of an act of desperation to try to fit to that curve. But in fact, it fits extremely well. It's a very precise curve, and it's a function of the Planck's that value of h can be determined from that curve. And I think he just plotted, the curve, uh, um, with multiple values of h until he got it to fit exactly right. And so that's quite a triumph. And also that allows you to determine what Planck's constant is. And it's a very small number, and that's why we don't see quantization of things and so forth. And this leads to this looks like some stuff having to do with the photoelectric effect.
Well, it's saying
And
like it needs to incorporate that in order to
so
derive it.
so this was a big mystery with Planck and other folks of that era. And then Einstein came along, and this was actually work that Einstein did before he
Mhm.
published on relativity.
The
Mm,
photoelectric effect.
this is called the photoelectric effect. And so sort of incorporating the ideas of quantized energy. um,
Right.
Einstein postulated or made this proposal that the energy of the photons is quantized. And so there were other experiments. There was a guy. His last name was Leonard, not Leonard, but Leonard, something like that.
Not you.
Not me. Yeah. Uh, but Leonard, who he discovered this principle, this idea about
Hmm.
um, the stopping potential. Actually, if you scroll back, I saw some of they had photocells then, and a photocell is it's not a it's
Stopping voltage here, you mean?
yeah, so they call
Right.
stopping voltage. And so the idea was, if you go back to the apparatus, there was a this no, keep
No.
going back. I saw no, yeah,
This thing?
yeah, this thing.
Yeah.
So this is a classical kind of thing. Um, so this explaining the photoelectric effect. So what that thing is, that vacuum tube, is
Hmm.
it's a piece of metal that's like a cup there, and I think it's labeled C. And
Hmm.
it's charged in a I think it's positively charged. And then there's at E there's a piece of metal, and they would use things like selenium or some other kind of very um, some kind of metal that can easily emit electrons. And what they found is that if you shine light on that object,
Hmm.
then a current would flow to the through that loop. And and then if you increase the potential, you could stop the current.
So,
And and
right.
it was thought that, so that's kind of like measuring how much energy that each of the photons has. And so it was thought, if I increase the intensity, I should be able to
Right.
increase
And
the
by the way, increasing intensity basically means you shine more of the same light on there.
you just make it brighter. And it was found that it doesn't matter. It doesn't matter how
Doesn't
how
do
bright
anything.
it doesn't it all it does is the it increases the current, but the voltage that current exhibits, the energy of those
Mhm.
electrons, remains constant. And so that's indicated by that stopping potential. What we expect classically is that the more the more the more intense the light, then the
Mhm.
more energy that the electrons would have, and so it would be harder to stop them. But it was found that no matter how bright that light was, and keep in mind, I keep saying how bright it was, not what color it is,
Right. How bright it is.
that stopping potential was the same. If you increase the frequency of the light, if you make it like
More
violet
blue,
light,
more
or even,
violet.
yeah, more blue, then
Mhm.
you increase the stopping potential. Actually, you decrease the stopping potential.
So it's like it's dependent not on how much light there is, but it's dependent on how on the frequency.
On its frequency. And so Einstein said, if I multiply Planck's constant by the
Mhm.
frequency, it equals effectively equals that stopping potential. So
That's right here.
right.
H times
Yeah.
nu, where
Yeah.
H is Planck's constant and
Uh-huh.
nu is the frequency of
Now
the
it's
light.
not quite it's not quite right, because there's also that W there, and that's something called work function. So work function has to do with another factor that requires a certain constant amount of energy to remove the electron from the surface of the
Right.
the body, and we can
But
talk about that another time. So
mhm.
this is something that you learn in, I don't know if you learn this in high school physics, but I mean you certainly learn this
When
in,
did you learn it, Leonard?
I don't remember. I think third
Well,
grade, but
third grade. All right.
yeah,
So for everybody out there, Leonard,
I
who you could learn this in third grade.
so
Okay,
no, I'm kidding.
know some basic
So
algebra is
yeah.
simple enough,
So
but
so so
yeah.
it's very interesting. Einstein came out and said, "Look, photons have a quantized amount of energy." And so that was putting all of the pieces together with Planck's
Hmm.
observation about Planck's law and the photoelectric effect that came from this experiment, because this experiment was done. People were trying to, they were trying to figure this out, and so
Right.
Einstein pulled this all together, and ultimately he won the. There it is. That's the equipetition. Um,
Which one?
Principle, that equation there. So you start doing that equation, and you can manipulate that into different ways to get the Planck's
Oh, I see.
distribution. But let's not do that. That's um,
Well, this just gets more and more math. Uh,
yeah. So
so and then
yeah,
this is what you mean by the infinite series right here. I
yeah,
think that's what you meant when
uh-huh,
you
yeah, yeah,
basically turn these
yeah,
summations into infinite series, and
uh-huh,
then you turn the series of these basically series expansions turn into this.
uh-huh,
You can rewrite it, and essentially you derive the average energy of a mode of frequency nu.
uh-huh, yeah,
And with that, you can plug it back in, uh, right?
uh-huh,
Yeah. So
yeah.
that makes sense.
So classically, if you have infinite number of modes, then it ends up just being equal to k times t. But if you have quantized modes, then it ends up being that other thing. It's kind of a neat mathy thing. I hope people agree that that's a you know
That is pretty neat.
it's kind of cool. Um, but
All right.
anyway,
So
so Einstein discovered so that's a black body. That's what a black body is, and real objects are really
are
not.
real objects black bodies? My
Real
question for
objects
you.
are not precisely black bodies. So, for example, people will say the sun is a black body, but in fact, it has some cutouts. Some absorption bands and so forth, things like that. A real black body, or the way a black body can be simulated, is to have a hollow um, material, like a metal can, and just drill a hole into it. And then that hole is a perfect absorber, or almost nearly perfect absorber of any photon that goes in. Will just bounce around and get kind of like lost in the, or absorbed into the radiation modes that are inside. A real body is not a black body because it has a tendency to reflect. So there can be reflections and some surface properties, some what they call emissivity. There you go. That was a good example of it. I mean, and the hotter it is, actually, I've observed this with like a metal can. I've taken a metal can and put it in the fireplace
What
with a
have you
hole in
noticed
it.
when you do that?
Okay, well, I can put a hole in the metal can, and then I
Uh
can
huh.
put the can in the fireplace and let it get really hot. And then
Hmm.
the light that's coming out of the hole is brighter than the light that is coming from the hot can. So the can is glowing reddish because I've got it heated up. But then the light that comes out of the hole is almost like white. And so that's representing the black body radiation, whereas the radiation from the surface, from a real surface like the metal, is
Right.
attenuated and disturbed by other kinds of things like surface coatings and reflections and
Got it.
and like
Yeah,
that.
that makes sense. Now,
Mhm.
in relating it to space, a lot of stellar objects are can be represented as black bodies, right?
Well, the cosmic microwave background that we've talked about is a very low temperature black body, and it is actually the most precisely tuned or most precisely um, um, calibrated, if you want to put it that way, black body that exists. Um, and it's at the edges of our universe. So there's
What?
parts. It's very profound, actually, that the the most distant surface that we could observe in the universe is a perfect black body, almost perfect. There are
What?
some imperfections.
Why do we say that it's like a near perfect black body?
Well, because when you look at a distribution of the radiation from it, it perfectly follows Planck's law.
Mm,
That
This is
and
an
and
interesting picture.
So yeah, and so the cosmic microwave background is what we see over to the right, and although
Mhm.
there's some inhomogeneities and little imperfections in it, those are extremely small compared to the overall distribution of the radiation, and it's like I said, it's a very stunning fact that an object that is literally the size of the universe, it's 14 billion light years away, is so precisely tuned so that it follows the black body law. And of course, like I said, the inhomogeneities and waves that you see there kind of makes it sound like I'm lying, but really those little perturbations are so small compared to the black body.
Right. I mean, go ahead.
I was going to say, see if you can Google black body curve of the cosmic microwave background. Maybe I've seen distributions of it. So
That's it's incredible that it's so
so it's
small of a
so so
difference.
so the universe is a black body,
Hmm.
or at least that we're inside of a black body.
We're inside of a
We're,
black
we're
body,
inside of
so
a black body cavity radiator.
so you're talking about like that metal can that you just stick a hole through, and we're like inside that metal can.
Yeah. Now, yeah, we're inside that metal can, except that metal can is really hot, because it's in the fireplace, and so it's
Right.
radiating in the visible frequency, so I can see, and you can do this. It won't hurt you or anything. I mean, don't touch the can; you'll burn you. But you know,
Experiment.
but
Yeah.
yeah, but you can do that experiment. You can take a can and not make sure the can is open. Don't put a sealed can in the fireplace because it'll explode. I mean, but if you just take an old can and you can put it in the fireplace and in the coals where the coals are and let it heat up. Of course, we don't do that in Houston, do we? But you can get a
Well,
barbecue. You can put it in the barbecue and let it heat
exactly.
up. And then if you make a little hole in it before you start, and you'll see that the light that's coming out of the hole is brighter than the surface of the can. But so these are objects that we see out there. It's thought that black holes would be black body radiators because they do have a temperature, but they radiate it very there it is. Yes. So the actual observation of the
So
cosmic microwave background
right.
is a very precisely calibrated or very precise it very precisely conforms to the black body radiation formula, and so
The colors. So most of it's uniform. That's what you're saying.
yeah, what I'm trying to say is that those colors represent tiny little imperceptible bumps
Hmm.
on that distribution. At different places. But overall, every place you look, it's
It looks
basically
about the
conforming.
same.
Yeah, and
Right.
the deviations, the error bars on that are some one part in like 10 to the 6th of the
So,
of the.
so essentially, if you're looking at cosmic microwave background, you'll say, hey, a 1 millimeter wavelength light, there would be approximately 2, I don't know, relative intensity, whatever that is, whatever units
I think
that
it's
would be.
it's just normalized to
Yeah.
the
Yeah. But basically, it's the distribution of light, the frequency, how much light there is with certain frequencies, follow
yeah,
that of a black body curve with an average temperature of
right.
2.725
And
kelvins.
that corresponds to a microwave frequency. So
So,
so actually the microwave frequency is very low temperature, even though you can use it to boil water.
hmm.
So that's a different principle. So
You
in the
said
microwave oven,
you were saying something about black holes? Is that a black body?
a black hole should be a black body to very high precision.
Okay, so a black hole is also emitting radiation then.
It's emitting Hawking radiation.
Okay.
That's something that's been discovered in the past. Well, it's been discovered theoretically. I don't think anyone's ever actually observed. I'm sure that no one's observed Hawking radiation.
Okay. No,
So
I mean it makes sense. So Hawking radiation is
and
just
yeah,
a black
and
body
yeah,
for black holes. Yeah.
and essentially the sun and all the stars are essentially black bodies, although they're not perfect. The people are black bodies. They have a distribution that's in the infrared.
Why are humans? Why are us? Why am I a black body?
Oh, because your temperature is about 275 degrees Kelvin, and if we were to do a distribution of the radiation that's being emitted from that
Oh
temperature
wow.
source,
How is
we
that?
would see that it had a similar curve to the
As
way the
right, Planck's law.
Planck's law. It would approximately follow Planck's law, not perfectly because different parts of you are tending to reflect light and would have different um, you know deviations from that perfect.
What is my? What did you say my temperature would be?
I
275.
I feel like it's 273 or 2 whatever it is in Kelvin. I can't do that in my head. So your temperature is 37 Celsius, so add
Mm-hmm.
273. So you're about 300 and some degrees Kelvin. Everyone is.
Okay.
I am too, you know.
So it's about black body radiation curve of a human body is about
Yes.
yeah. So 37 degrees Celsius, right?
Yeah.
Right, and just
Mhm.
turn that into kelvins, right?
Yeah.
Which is 310 kelvins, right?
310. Okay. So people are 310 Kelvin. Everybody's about the same temperature.
So we're
So
all basically absorbing radiation and emitting it like a black body, or
not only that, but actually we have a little fire inside of us that's internally heating us. We're
okay. So
we're burnt. Yeah,
it doesn't even matter. I mean,
right.
I don't need to absorb that light up
No,
there
you
to
don't
be
need to
emitting
absorb the
that.
light. That's right. You'll it doesn't matter what temperature your environment is. You're always going to be unless you freeze to death, in which case you will assume the same temperature.
Okay.
So
So that's incredible. So a human is actually we're all like emitting radiation
we're all emitting radiation in the infrared.
in the
Infrared
infrared.
is a lower frequency than visible light. Some people talk about like we could start talking about crypt, what do you call cryptozoology and like Bigfoot and
So
temperament. Yeah,
if humans' body temperature was actually higher, then at a certain point somebody could be glowing.
that's right.
Like you would see their visible
You
light.
you are glowing, okay, and if we have the right kind of equipment like infrared,
Oh, that's right. That's how
uh,
you can use the infrared sensors or
right.
goggles, right?
Well, yeah, and actually the military uses that for what the military does. to there's night vision and some night vision equipment is infrared, but some of it's also just like low light amplification. So
Right. I just found this random picture. I don't know why, but
right,
that
so
actually shows something.
so that dude, he looks like he's pretty sleepy, doesn't he? But I can't.
Yeah.
Well, his eyelids seem to be really hotter than I would have expected. But any anyway, yeah, he's a black body, right? But he's
Right.
not perfect. So he's got different temperatures in different areas. They have a background there. It looks like that's a radiator of some sort. And so they pointed to that as a black body background. But but it's sort of a little bit of a misnomer. It's just saying that's a black body radiator because it's kind of like designed to be kind of uniform, but every part of this person is going to be approximately
Hmm.
distributed according to the Planck um, law. You like
Yeah.
this? This seems to please you.
Well, no, I mean it's interesting. I actually have never thought about it,
Yeah.
but I always thought, oh, black bodies. That's referring to the stars and cosmic microwave background and black holes. But I never thought
Yeah.
light bulbs,
The
incandescent light bulbs. But I never
incandescent
thought,
light bulbs. Now
right?
the new light bulbs that we're getting, the LED light bulbs, they are not black bodies. And if you were to do the
Why?
why? Because they rely on a principle that produces very very tightly tight frequency um, physical principles that emit light in a very narrow range of frequencies. And in fact, it's usually they're mixed so that you have some red and yellow, and they've even figured out how to do blue recently within the past 15 years. And so that's why our what do we call them? Those kind of lights
Hmm.
are
LED lights.
the LED lights are we were able to get some that emit white light, and the quality of them has improved, greatly in the past, really in the past 5 years. So that because there's been some developments in ability to produce blue light from LEDs and so forth. So so
That's
those
actually.
are
Mhm.
those
Go
are
ahead.
those are not black body because they rely on a different principle. They don't emit at multiple wavelengths. What do you have? You have an LED here?
Well, I mean, we
Yeah.
have like daylight, incandescent, fluorescent, and LED.
So
As you
which
can see, go ahead.
Oh yeah, there. You see the incandescent is that dotted curve and goes off and it follows
Yeah, it
that
follows it.
long curve, and it's emitting at
Yep.
at higher
Oops.
frequency,
Sorry.
actually lower frequency, much more. So this is inverted. So the wavelength, the longer wavelength is the lower energy, right?
Right.
So it's a little bit inverted. But there you can see there the different kinds of fluorescent and LED, and that's a tremendous advantage because what that does is it allows you to really tailor the light that you need for seeing just in that narrow range of frequencies that people are able to see. Most
Because
of
we
the
can't
energy
see infrared,
we
and most
can't.
of the light is in
Mhm.
infrared, right?
And
Yeah.
most of for incandescent bulbs, they
Yeah.
get really hot, right? And everybody knows that. And it's sort of wasteful if you need to air condition, if you need to do air conditioning.
Right.
So it's much better to have those. I've been gradually. I still have a few incandescent bulbs that haven't burned out yet, but I've been replacing all in my house.
You can see like I mean, people use LEDs because if you look at the graph, like most of the wavelength that has the highest intensities are those in the visible light range,
They're in
which
the
we can
visible
see
light lane, and
easily.
the manufacturers have been able to really carefully craft that light appearance so that they look very attractive and are not harsh or um, you know
Right.
so actually the lights that are in my that I'm being lit by right now are almost all LEDs, except for there's a fluorescent in the room here as
I find
well.
it interesting. Isn't the daylight? It shows that that's the topmost curve. And that
Well,
one, I guess, is like a black body, except that's due to the sun, which has a much higher temperature, right? And so that's why.
so that's why it's shifted all the way over to the left. It's not the best presentation there, but that's what
Well,
they yeah. So
okay,
yeah, daylight is a 5500 degree Kelvin
black body,
radiant
right?
black, and it's approximately a black body. It does have some distinguishing bite outs or absorption bands in it. So especially in the atmosphere, from the atmosphere. So daylight in particular doesn't have as much ultraviolet. At the surface of the Earth, daylight doesn't have as much ultraviolet as the sun does, because a lot of the ultraviolet is filtered out in the stratosphere.
That's actually really interesting to note. You might be wondering, okay, I was actually trying to find a better picture depicting something, but
Okay.
this one might be good, perhaps. Oops, does it show up?
There you go.
There we go.
So here we see several different blackbody radiation curves, and so that red one is approximately what the sun does, or maybe a hotter star than the sun. The next one down, which is a black line, that's just a little bit cooler than the sun, and you see the amount of visible light we get from it. And then so the lower temperature ones, so that 4,000 Kelvin one, that would be like maybe a very hot fire that you have
Right.
burning in the fireplace. 3,000 Kelvin would be like a fire, and so there you can see the distributions there.
The hotter your surface is, the more light you are at a higher frequency or lower wavelength.
Right. And so that the green one down there, that's like the temperature of your stovetop, say. That's how hot the stovetop. Maybe it's a little hotter than that. And so you're only getting a little tail of the where it's coming into the visible range there, little tail of that distribution. So it's just exciting the red light. And so you can see the infrared and then red. So infrared is kind of like the heat energy, the heat temperature. So that's actually a very interesting figure. The sun has a lot of ultraviolet, and you can see that's to the left of the visible range. So the sun would be represented by the black and maybe the red curves. The sun is somewhere between those two curves.
Right.
And some stars may be very much more intense than that.
Right. Just depends on how hot their surface is.
Exactly.
Either your peak frequency, your peak intensity, the frequency with your peak intensity is shifted either to the left or to the right.
That's right. And so actually the peak frequency is a characteristic of the temperature, and the lower the temperature is, the further to the right it will go, be moved. And it's actually proportional. Let me see. The total intensity is proportional to the fourth power
of the temperature.
And
that's Stefan Boltzmann law, right? Yeah.
Okay. Yes. I don't remember. That's probably right. I don't remember if that's, but I do remember, so I think of it as, that's a well-known thing, that the temperature, the total emission, in other words, the integral of the total amount of energy being emitted by each of these black bodies, is proportional to the fourth power of the temperature. So
fascinating.
Anyway, that's about all I know.
I mean, I think you know quite a bit. Like, this was quite a physics and slightly math heavy episode. Not that much.
No,
math.
It's not math. Don't worry about the math. It's the
don't worry about the math.
Yeah, don't worry about the math. It's like, it's just the ideas that are Stefan Boltzmann law, and sigma is emissivity. So that's like a surface property. The sigma in that formula there, sigma times 10 t to the fourth power. And different objects have a different amounts of emissivity and that affect that. So
you can So with all that said, all right, we are going to have to wrap it up, right?
Oh, did you want to talk about anything else, or?
I mean, shall we? Let me see.
No.
What do we have?
Well,
I can't imagine what else is there to talk about.
No, neither can I.
I mean, it'd be nice if I was. Let's see here. You want to?
I started
There
to
was
talk. I started to talk about Bigfoot.
okay. Have you seen a Bigfoot?
No, I've never seen a Bigfoot, but people have said that they have infrared vision.
Bigfoot has infrared vision.
I've heard that. I've read that. I've read that they have infrared. You know, and so I want to point out something that would mean that they're not a mammal. Okay, that means that they're cold-blooded, because in order to have infrared vision, you need to be you need apparatus, you need visual apparatus that's at a lower temperature than the things that you're viewing.
Okay, so for Bigfoot to have infrared vision,
He would need to be cold. He'd need to be colder than the things that he's looking at.
okay, so
Certain kinds
interesting.
certain kinds of snakes, highly evolved snakes like rattlesnakes, they do have a kind of infrared eye that's below their regular eye. It's like a pit. That's why they call them pit vipers. And the little pit there has nerve heat sensing nerves in it, and they're able to detect
But
infrared, but that's dependent upon them not having an internal temperature. See, because
let's see. Speaking of Bigfoot,
there you
let's
are.
go with this. Internet left divided after two men claim to have captured Bigfoot on camera. Oh, I thought it was captured Bigfoot. I was getting excited, but it's just on
Yeah,
camera.
yeah,
Wait, does that look like Bigfoot to you?
absolutely. What
I
else could
mean,
it
what else
be?
could that be? What else could that be?
I
I
don't
mean,
know.
it's two men claim to have captured video footage of Bigfoot as it drove through a forest. Video posted by Cryptid University on TikTok has
Yeah.
received. This was like posted last May. All right, so I don't know.
So
It's still
what
up
is
there.
the Bigfoot alien visitor connection? Is there one? Is there a
I don't know. I mean, some people. I told you a conference a while back I was semi interested in attending was a combination of UFO enthusiasts and Bigfoot.
Oh, I want to
Bigfoot
go to
people.
that conference.
You do?
Yeah. Did they have you didn't go to this?
No, I didn't. I found out too late.
I wonder if we should cosplay. You know, we we could dress up like Bigfoot, or dress
Oh
up
my
like
gosh.
aliens.
Oh man,
So,
that's
yeah.
that's so funny. Okay, well, could definitely look into that. I suppose. I mean,
Okay.
what other things can there possibly be better than just cosplaying, other than
Cosplay
Bigfoot and
as Bigfoot,
aliens, right?
right? Bigfoot and aliens. Yeah. So
It's interesting how such a conference actually exists, like
I
the
think it's
combination of the two.
I think this is a great country.
Oh, actually, you know what? There's one that just happened. Let's see here. So I know we're gonna hurry this up soon. But look, in North Carolina, UFO Bigfoot host convention for all things cryptid.
All things
So
cryptid.
so they assume that Bigfoot's like a unknown creature, right? And
Uh-huh.
UFOs with aliens, assuming that's what you think, are also unknown creatures. So hence, why
Why
not?
not have a convention about unknown
Exactly.
things? Yes.
The
I
unknown, like little cryptids. That's what they call them, I
Yeah.
guess.
I don't, I guess I can't really help but to make light of it a little bit, but I mean, it's okay. It's, you know, I would go, you know. I don't believe that there is a Bigfoot, and I don't believe that there are aliens. But the Bigfoot one is because
Oh,
there
too
there
late.
there are more cameras on Earth than there are people.
Then there are people. Well,
And
they have the blurring technology.
right.
Yeah,
So
that's that explains a lot.
and it is possible to exclude Bigfoot if you look everywhere. If you're able to look everywhere on Earth, you should be able to zero out the probability that Bigfoot exists. You can prove a negative. It doesn't exist because we've looked everywhere. So
Oh my gosh,
anyway,
is there one coming up?
May
I don't know if I
May
can make it,
May
but
19th. Where is
where
that?
is this place? Oh, I think it's in North Carolina. It looks like.
Oh
That's so
yeah.
funny. Since I was following from that link, what is the what is the catchphrase? Come a skeptic, leave a believer.
I
I'm
so
sorry. I'm
yeah,
not
I'm sorry.
saying I tend to have a pretty open mind, so but
I do
it's just
too.
funny.
I do too, and I'm sure that I would enjoy going to the Bigfoot Tracks ice cream fest, whatever it is, whatever they're doing.
Well, this looks more
So,
like a festival. I think this, a
uh-huh,
lot of people seem to be having fun.
and
Looks like
and
you
and
could dress up. Look at that.
and the strange and like curious characters that you could meet, the kind of people that you would
Just
meet there.
imagine, right?
Mhm.
All right,
Yes.
maybe next year. But
All right.
hey,
You're
if
hungry.
anybody of
You're
our listeners are actually in that area and you're interested, you can go May 19th and May 20th, 2023. So that's something. All
it's
right.
coming up.
With that, we kind of went over time again. Normally,
That's because it's
I'll
so
play
much
some
fun.
ambient music, but there's no sound apparently coming from this, so that's fine. I'm gonna go with the Namaste. Look up because you never know what you will see. You might see, well, a black body object like the sun, or you might see another black body object like Leonard there, or, well, you're not gonna be up. You're just gonna be around. But anyways, point is, who knows, right? Support the show, patreon.com/SG2 on space. We will be
Like,
back next week. You can catch it at youtube.com/@Shingo/streams. So thanks everybody. And next Tuesday, 6:37 p.m. And what do we always say?
we say moi.
Namaste. Okay, that's what you
Mwah.
say. There we go.
Good night.